So here we are on April the 2nd, and we're into comparing averages or means. We're going to do this today. We did it before. We're going to do it again, and then hopefully talk a little bit about other stuff and get everything all squared away and beautiful. It's a theory anyway. So make sure we get most people accounted for here. All right. So I guess we're going to make it all happen. We made it all happen yesterday. We're going to make it all happen again today. Until we get to that point where it's all happening. First of all, get rid of this. I want to know the different kinds of hypothesis testing and confidence intervals that we started with. Scott, can you tell me? Okay. Carter, can you tell me?
Single sample.
Okay, we start with single sample. Zach in the front, what does that mean? Or what are the different kinds of single sample hypothesis tests?
Portion.
Portion is one, what else?
Or mean.
Mean, and? Okay. And what's our goal with hypothesis testing in all these situations?
The alternative.
No, sorry. Dylan, what's our goal?
To prove a difference from a standard.
Okay, we want to prove a difference from a standard, which is the alternative. But in all these situations, we're proving the difference from a standard number. Okay. Can we use confidence intervals to do this? Cam?
No.
Wrong answer. Hey, can we use confidence intervals to do this?
Yeah.
Yes, how?
Use it to measure it.
We are using it to measure what?
This portion or standard.
There's a word that was missing.
So this proof distance between two groups.
No. This is single sample. Okay. The confidence interval measures what? Yep.
It measures where the population, if we're measuring population proportion.
Okay, it measures something about a population.
Yeah.
Okay, so confidence intervals measure something about a population. How do we use confidence intervals in order to prove a difference from a standard? Jaron, can you tell me?
We compare the standard number or something to each of the confidence intervals to see if it's within
Okay,
or lower, higher.
that's correct. So if the confidence interval does not contain the standard number, then we prove a difference. Okay, so we're able to do hypothesis testing with a single sample, trying to prove a difference from a standard number, and we can do either proportioning or standard deviation. If we use confidence intervals, we can do the same process, but here we're looking to see if the standard number is outside of the confidence interval. In other words, if the standard number is outside the confidence interval, then the confidence interval is telling us what's really happening, and it is different from the standard number. Try to remember, the thing that we're getting is the confidence interval. The confidence interval is measuring something about the population. That's what we want to talk about. We want to talk about where the population number is, and that's in the confidence. Okay. Karen, what's next after single sample?
When we do two sample,
Okay. Megan, can you tell me the different kinds of two sample testing we do?
Two proportions, two standard deviations, two means, and one paired data.
Okay. And Megan, can you tell me what we're trying to do when we do hypothesis testing for two samples?
Prove the difference between two data sets.
Okay. Not, kind of, but not really. We actually want to prove the difference between two populations. We know that the data sets are different because they're always going to be different from each other. What we want to know is our populations different from each other. Okay, not just the samples. Okay. Can we use confidence intervals for these, Alden?
Yeah.
Okay, how does that work?
Use confidence interval, and if your confidence intervals for each sample don't overlap with their population, improve the difference.
Okay, if the confidence intervals don't overlap, then that proves the difference. Now, this doesn't really apply to the paired data because in the paired data, we actually just make one data set from that. So paired data does not have two separate confidence intervals. So no confidence interval. It is possible for us to use the paired data in comparing it to a standard number. Okay. This would be a difficult question perhaps to answer. If we're doing paired data, what's the standard number to which we compare?
Would it be the average of both?
No. Right? We're looking at the differences, right? When we do paired data, we get the differences wrong. So the standard number we're comparing to is 0. If it's greater than 0, then the difference is averaged positive. If it's less than 0, they would average to be negative. So really, when we do paired differences, paired data, we're comparing it to the standard number of 0 to say, is there a positive difference or a negative difference when we do that. So in that sense, it doesn't quite follow the pattern that we established. Okay. What else? Back in the back, what do we got next? Multiple sample or multiple comparison? Right. Josh, do you know what the 3 kinds of multiple comparison are? Okay. Scott, can you tell me what the three kinds of fault comparison?
Goodness of fit, test of independence, and ANOVA.
Okay. All right. So, Chelsea, what's the null hypothesis for goodness of fit?
Null hypothesis is proportions match given set. And the alternative is at least one population proportion is different.
Okay. Okay. Zach in the front, what about test of independence?
The hypothesis for that would be, null would be that they're independent.
Okay.
And then the alternative would be that they're T.
Okay. What does that mean? Zach?
Well, independent means that the outcome of one would affect the other.
Okay.
And then dependent would be vice versa.
Okay. The outcome of one does affect it. Right. Okay. How about ANOVA, Dylan?
The null alternative,
Yes.
that'd be, I can't think of what it is, but like the U1,
Mu.
mu,
Okay.
mu1 is equal to mu2, and so on, how many you have, and then,
We have to have more than two, so yeah. Okay.
and then the alternative would be at least one mu is different.
Okay. Carter, can we use confidence intervals for part A? Goodness of fit?
Yes.
Yes, we can. How does that work?
So if our p-value is not in the interval, it's either higher or lower than we expected.
No, but close. Okay. If the P is not in the interval, comma, can somebody fill in the rest of the statement?
We reject the null hypothesis.
Okay, so then what does that mean?
That means that, what does it mean when we reject the null hypothesis?
Yes.
That we have enough evidence to prove at least one of our proportions.
No, that was the alternative here, which just tells us that there's something that's different. But over here, once we use a confidence interval, we can be more specific about that. So then the question is, what does it actually mean if P is not in the interval?
They're different.
Okay, but there's more to it than that.
Could you say it's like more or less than what we expected?
What is more or less than we expected?
The like proportion.
Okay, but what are we specifically talking about? And I'm going to tell you the answer because it's not fair for you to read my mind all the time. Okay, if P is not in the interval, then the interval is higher or lower. I should say that the interval for the population proportion is. Okay. So what we're talking about here is if the P that we're given, this is the given P. If the given P is not in the interval, then the interval for the population proportion is either higher or lower than we expected it to be. They are different, which is what you said, Scott. Yes, they are different, but the fact of the matter is the interval tells us what's really happening compared to what we thought would happen from the given. Okay? So let's make that happen here. You've written this down, right? So eliminate all that. So here is an indication of accidents in Denmark for different days of the week. Okay. And I adjusted this. I fudged with it. I messed with it so that the n came out to be 1,400. And so if they were all equal, that would be 200 each time. So this would be divided by 7. And as we said last time, if it's 1/7, then this is my proportion I expect it to be. 14.3% is 1 divided by 7. So then 1/7 of each of those gives me 200. These are my observed, these are my expected. Here's my chi-squared. It's a big number. I reject the null. So at least one of these is different. Chi-squared tells me that there is something which is different. But now I'm going to look at the confidence intervals. Okay. So I'm looking at confidence intervals here. What am I comparing them to? I'm comparing them to this percentage. This is 1 divided by 7, which is 0.143. This is what I expect the proportions to be. Are they or are they not? That's what I'm asking. Okay. So, Dalton, what can you tell me?
Specifically, like, seems like for stuff like Sunday, it's frequency would be lower.
Yes. So if I look at Sunday and I look at the confidence intervals, the confidence interval for Sunday is completely below this 14%. So that means there are fewer accidents on Sunday than what I expected it to be. Okay. Jaron, anything else?
And then for Friday, it's higher than you expected.
Okay. So for Friday, this interval is higher than what I expected. Is there anything else I can say? Jeff?
You'd say that Wednesday is also, oh, no, I'm sorry. That the rest of the days fall into that percentage. So other than those 2 days, that everything else falls within what we expected.
Kind of, right? So the fact is that we can't say anything about the rest of the day, okay? Because we say no decision about the rest of the days. Because the confidence interval is telling me where the population number is. And for any of these, it could be either higher than or lower than. I don't know. So I have not been able to prove a difference for any of the other days. I cannot say they are the same, but I can also not prove that there is a difference. So what I have right now is that the number of accidents is lower on Sunday, but it's higher on Friday. Why do you think that would be the case?
Because people are at church on Sunday.
Yeah, okay, we did that last time, right? So we know that, people at church on Sunday. What about Friday?
People are going out, drinking.
People are not at church on Friday, right? Okay, so they're doing other things. And it's all pent up after that week, right? They've been working all that time, just looking forward to that chance to go out on Friday and have an accident.
Yeah, but this is in Denmark. It's not-
Oh, yeah, well, Denmark, they have accidents in Denmark.
Yeah, but
Yeah.
I think Friday, they don't actually work on.
Oh, then nobody works on Friday in Denmark?
Yeah.
Well, maybe they don't go to church. Oh, we never even thought about that, right? Okay, I don't even know about Denmark. Their church going on. Hard to know, but anyway. We don't know the answer to the question that I posed, but hey, we could speculate. But this would be something that if you were a social scientist, right, or you're in charge of keeping people from having accidents or rescuing people or something, this would probably be information you'd want to know. So then that's how this works, okay? Chi-squared did not really tell us the information that we wanted. Chi-squared told us that there is a difference. Now we have a better idea of what those differences are. However, as I mentioned, what we just did was relatively illegitimate because I'm comparing 7 different confidence intervals to these numbers. What's 0.95 to the 7th power?
With them?
70%? So that would mean this is my chance of being right, 70%. Well, that's not very good. I could be wrong about these things. But the fact of the matter is, chi-squared told me there was a difference. And now these confidence intervals are telling me where the difference is. So it seems reasonable that I would find a difference, right? And so then it seems reasonable that I would find it where the confidence intervals tell me it is. But I run into trouble. I could be making an error here. And so if we really want to do this, we would have to use more sophisticated possibilities, which we're not going to worry about. And again, which we talked about earlier, it might be that the confidence intervals are actually telling me a thing that's meaningful. Whereas the other idea that I had before might be making some assumptions that I shouldn't be making. So anyway, here we are. And we found stuff and it's interesting, right? Good. So that is the process of doing that kind of a thing. What about this test of independence? Can we use confidence intervals for the test of independence? Nope. Oh, not good. Chelsea, can we do that?
I think so. I didn't write it down.
Okay. Megan, what do you think? All right. Ake, what do you say? Okay. Dylan?
Yes, you can.
Yes, you can. How would that work?
Well, I don't know for sure, actually.
Okay, all right.
I could guess.
You have great confidence about confidence intervals, all right? So what's your guess?
I would say maybe that, like, if the confidence intervals, if a certain value isn't contained in those intervals, then you'd say that they're dependent and not independent.
Because what we're talking about here is that the categories affect the proportions, right? And if they affect the proportions, then you would expect them to be different, right? And so then a confidence interval, you would expect differences between the confidence intervals, right? Well, that's possible. So let's take a look here. We talked about this problem about whether people under 30 supported Clinton or Trump, and we found that they supported Clinton, but just by a little bit, where people from 30 to 44 were large supporters of Clinton. And then the 45 to 64 were large supporters of Trump, and then the 65 were just a little bit supporters for Trump, not very much. Which was not what I expected. I had expected it to be age dependent, younger for Clinton, older for Trump, but that's not what happened. Specific groups of people, 45 to 64 went for Trump, 30 to 44 went for Clinton, but the other two groups were more evenly split. Now, how would I use confidence intervals for that? Well, let's just look at what we have here. This is 60% for Clinton, but that's between 55 and 65. This is 42% for Clinton, so that's 39 to 46. So it looks like this confidence interval is separate from this one. So I would say this confidence interval is lower than this. So I would say there's a difference between the two, right? That's how you would do it, okay? But notice, if I'm comparing these two confidence intervals, I have to think about the fact that I'm comparing all these confidence intervals. So I'd be comparing this one with this one, this one with that one, this one with that one. So I'd be doing 10 comparisons here, right? But then I also have the columns. And those also generate confidence intervals. And so then I have a lot of these confidence intervals too. And every time I do a comparison, I increase my chances of being wrong. So yeah, if I use confidence intervals with the test of independence, I might actually find something. But I've got so many different things going on that for me to say, well, I know what I'm doing here, would be kind of hard. Yet, chi-squared tells me something's going on. Chi-squared tells me, when I do this, that there is a difference, that these categories are different from each other. There is a relationship between the age category and the choice of who they vote for. So, I'd have to actually be kind of like a professional to do this. I'd actually have to know what I was doing. But it seems reasonable that I would just look at this and I say, the 30 to 44 went 60% for Clinton. 45 to 64 went 42% for Clinton. And when I run those numbers, it does look like that's a significant difference between the two. I don't have to necessarily compare all of these. So there's a difference here between what we might be able to prove mathematically and what we just look at and it just makes sense to us, right? It just makes sense that those numbers are different. And then if we put them through a confidence interval, we can say they are significantly different. But it's hard because there's no justification mathematically that we would pick those two. Why couldn't we pick all of them? Why couldn't we run them all through a computer and see which ones work? So this is where our experience comes in, where we say, I do see the difference, and I'm able to show these confidence intervals are separate from each other. And I'm not going to worry about the rest of them because it's pretty obvious that these are the ones I'm going to compare. And certainly if you look at this and you say, well, did older people go for Trump? The 45 to 64, is that bigger for Trump, which would be over here, compared to the 65 and over? Well, they were 58 for Trump, they were 51 for Trump. Is that a big practical difference? Well, it kind of seems like a little bit surprising. But what difference does it really make? If I were to ask the question, would you say that people 65 and over do not support Trump as much as you thought they did? Well, it depends on what you thought, right? So there's not an easy mathematical answer to say, how do we use confidence intervals for this situation? But it does seem reasonable. We can see a difference. And then we have to ask the question, is it a significant difference? All right, so that's that. So now we have at least an idea of confidence intervals, but I'm not going to expect you to do that. Okay? I am going to expect you to do this. We are going to do on our last project, we are going to have this goodness of fit thing, where you need to be able to match the categories and say, if the given P is not in the interval, then that means our population proportion is either higher or lower. But I want you to do this. We don't have to worry about this one here. How about ANOVA? Can we use confidence intervals for ANOVA? And what would that look like? Cam, what would you say about using confidence intervals for ANOVA?
I think you can.
Okay, so what would you look for here?
What you see, feel like it fits in the confidence interval.
If what fits in the confidence interval?
What is it? Is the F value? Or the
No.
P value?
No, neither of those things. Scott, what would you say about using confidence intervals for ANOVA?
Right over down.
All right. Carter, what do you say?
Yeah, I passed.
All right. Chelsea?
I know you can use them. I don't remember. I think you said they are, so for ANOVA, we want the means to equal one another.
That would be the null hypothesis. They are equal, okay?
So would we be looking for confidence intervals that do overlap?
No. Sorry. You were so close. You just forgot one word. We're looking for confidence intervals that do not overlap,
They do not.
okay? Because, if you may recall, if confidence intervals do not overlap, then that proves a difference. Here we are comparing the different ones, okay? There's not a standard number that we're comparing to. We're comparing them to each other. So if the confidence intervals do not overlap, then we prove a difference. So that's the same thing here. All right.
What was that picture you showed us then yesterday with all the averages and
Yeah, so then if I have averages that look like this and this and this, right?
Yeah.
So then if this confidence interval is here, and this one's here, and this one's here, then they would be different,
Okay,
okay?
Yeah.
The confidence interval doesn't have all the data,
okay.
but it would have 95% of it, right?
Right.
So yeah. All right. So what I want you to do is to go to page 641 in the textbook and do problem number 11. And what I want you to do is to use StatCrunch to do ANOVA and confidence intervals. And if you click on the little world symbol next to problem 11 in your e-textbook, it'll take the data and put it right into StatCrunch. So that makes it nice. All right, so I want you to work together now. This has now become a group project. I want you to find somebody around you that it can either help you or you can help them, all right? Either way.
this thing right here.
Mm-hmm.
Yeah. Whatever that is. I don't know if that's correct. I feel like it is.
Okay, not Tukey, okay? We're not talking Tukey here or Turkey. We're talking confidence intervals, just regular old confidence intervals. Right? All right, so let's see what we're talking about here. What are we actually measuring? It's always interesting to ask that question because most people, when they do statistics, don't know what they're measuring. So let's find out. What are we measuring here? Dalton, can you tell me? Okay. Zach in the back, can you tell me what we're doing here?
We're studying the effect of varying levels of medicines on a child's ability to follow rules.
That's correct. And if they have a higher score, that means they have a higher ability to follow the rules. Okay? And if you're living in an institution, like I am, then following rules tends to be a positive idea. You want people to follow the rules because you wouldn't make them rules if you didn't think they were good, usually. Unless you have some kind of a weird pain-inflicting desire to cause people grief. But there's nothing in here whether this is ethically right or wrong. It's just a matter of what we are measuring. So we're going to see if that works here. I mean, I don't want to go too far with this, but there are all kinds of people following rules who have done all kinds of horrible things. So following rules doesn't mean you're a better person necessarily, okay? Just so you know. Anyway, I'll put back my institutional hat and say, yes, follow the rules. So what we're looking at here then, if we do a ANOVA on this, we want to use StatCrunch. Megan, can you tell me how to do StatCrunch for ANOVA here? Okay.
In one way,
Right.
and then I just highlighted all of them,
Okay.
and then I hit compute.
Okay. So what does this tell us?
The average percentages that the children behave.
Okay, there's something going on and it has to do with children and their behavior. Jaron, can you tell me what this means here?
It just gives you the mean of their ability to follow rules.
That's what the first part does.
And then for the
Okay, let me just stop for a second here. This first part where it says column statistics, you should not believe what that says. Okay, that's not what we're going to focus our attention on. Even though it's there, it's not telling us what we need to know. Okay, so Jaron, continue.
then I do not know what the ANOVA table.
Oh, okay, well, we'll find out. Ake, can you tell me what's going on with the ANOVA table here?
Is it something that stats?
No, actually it's not. Dalton, can you tell me what to look at with the F table here, or the ANOVA table? Trying to get some help there, but not working. Okay, Dylan?
Do you look at the p-value?
I do. I look at the p-value. Okay. Alyssa, can you tell me the decision rule for p-value tests?
Less than, the confidence,
Alpha.
then rejected,
Reject what?
the null hypothesis.
And what happens if I reject the null hypothesis?
When you have sufficient evidence to prove that,
What does say prove the alternative? Okay. So, Dylan, is the p-value less than alpha?
Yes.
Should I reject the null hypothesis?
Yeah.
Should I prove the alternative?
Yeah.
Okay. Zach in the front, what does that mean?
What is proving the alternative?
Yes, in this situation.
Well, proving the alternative would be I'm not sure. I forget what the alternative for ANOVA is.
All right, so that's what I need. Cam, can you tell me what the alternative is for this?
I don't.
Okay.
at least one is different.
Okay. So that's what this is telling us. At least one of these averages is different. It does not tell us which one, and it does not tell us the direction of the difference. All it says is that there is some significant difference here in the average of the rule following ability based on different kinds of medicine that you take. Okay. So we are now done with ANOVA because that's all it can tell us. All right. Now I need confidence intervals. Carter, what can you tell me about confidence intervals here?
If they don't overlap, then we prove the difference.
Okay, how am I going to find confidence intervals using StatCrunch?
Did we already find them?
We did not.
So from there, go to edit.
Nope, sorry, we do not. Okay. If we did, go to edit. We do not have confidence intervals here. So, no. Chelsea, where am I going to go for confidence intervals?
Go to stat,
Stat,
and then t-stat,
t-stats,
one sample,
one sample
data.
with data. I select all my columns. And I do confidence interval for mean. And I compute them. And there they are. Okay. Scott, can you tell me what I'm looking for here?
Sample mean that doesn't fit in the lower or upper limits.
No, actually I'm not. Jeff, can you tell me what I'm looking for here?
We're looking for a single confidence interval that doesn't overlap with the rest of them.
True, but it doesn't have to be a single one. There could be multiples.
Yeah.
I'm looking, but that is what I'm looking for. I'm looking for confidence intervals which do not overlap. Okay. And certainly, if one doesn't overlap with the other one, then the other one doesn't overlap with that one. So, right. So there have to be two. If there's going to be a difference, it has to be two. Right. Now, I've said this a couple of times, but I'm going to say it again. I've taught this class for a lot of different opportunities, and many people do not get this until they do. And once they get it, it's very easy. It's so simple. But until you see it, it's like, this is impossible. I have no idea what's going on. I want to find intervals that do not overlap.
Placebo doesn't overlap with either of the Adderalls.
Because the upper limit here is 58.8, which is less than the lower limits of these two. Right. So then how I would say that is the mean of the placebo is less than the mean of Adderall 7.5, and the mean of placebo is less than the mean of Adderall 12.5. Is there anything else I can say?
No.
No. What I have to have is that the upper limit is below one of the lower limits. This upper limit is below these two, but none of these are below any of these. So those are the only two things I can say. So what do I think about Adderall at this point?
It has better rule following
Effects.
effects than placebos do.
Yeah. Is it good for us to compare to placebos?
Yes.
Yeah. We're supposed to use placebos because then it's not just a thing, it's a thing compared to a placebo. And placebos, we are eliminating the placebo effect by doing this. So yeah. Somewhat interesting though that, well, anyway, we'll just leave that. So I've been able to prove a thing here using confidence intervals, which tell me which averages are higher or lower and the direction of the difference. When I did ANOVA, even though I can see that the placebo mean is less than the other ones, I don't actually know if it's significantly less than any of the specific ones. When I do the confidence intervals, then I look at that and I say, well, the placebo is significantly less than the Adderall, but I'm not sure about Ritalin. Because for Ritalin, it could be that the average is 52 and for placebo is 59. So therefore, I really cannot say if it's greater than or less than because it could be either way. Now, this was using confidence intervals in order to make this happen. There is a thing in your textbook which is called Tukey's test. So we're going to take a look at Tukey here. It's not something I'll expect you to do, but it is something that we can do, and that is compute Tukey. And so when we compute Tukey, we get Tukey. I mean, it makes sense, right? What Tukey does is that it assigns a p-value to the differences between the averages. And so when we look at this, according to this, the p-value is under 0.05 for Ritalin as well as Adderall. So therefore, we would reject the null hypothesis for the Ritalin as we would for the Adderall. So then Ritalin would also be seen to be effective as well as Adderall. But it's pretty clear that Adderall has a higher chance of not being, or let me say this. It looks like the results are better for Adderall than they are for Ritalin because these are lower p-values. And then there's nothing else in terms of p-values to make this happen. So once again, what we are saying is, if I use confidence intervals, it's a different way of looking at the results. And it might be, some people say, that confidence intervals are the better way of looking at these results as opposed to using what we just did with Tukey. So then we would say, well, the confidence intervals tell me this, so this is what I'm going to believe, where the other thing I'm not quite sure about, but people have different opinions about whether that's a good idea or not. All right, now, for next time, what I have listed here on the schedule is that project 2-3 is due on Thursday. This is flexible deadline, okay? So if you are able to get it done, that's great. And if you're able to turn it in, that's also good. Then if I find something that's wrong, hopefully I will go through and be able to tell you, and then you'd be able to correct it if you want. But that's what's going to happen next time. And then we'll move on to the next chapter and start in talking about that.